Okay, I suggest we start. Welcome everyone to this instance of Verifiability Talk series. It's my honor to introduce Rob Hierons, who is also a work package lead in our project on verifiability. He is a professor of software testing at the University of Sheffield, and he has extensive expertise in various areas of software testing, including model-based testing from finite state machines and search-based testing. And today he will talk about an application of mutation testing in testing robotic software. Rob, thank you very much for having accepted our invitation, and the floor is yours.
Okay, thank you very much, Mohammed. Thank you for the invitation and the introduction. So yes, as Mohammed said, I've been today to go through at a fairly high level an approach we've been applying to test generation. This is being within the RoboTest project, which also involves the University of York and the University of Surrey. So I'll touch upon obviously the motivation and then the approach with two main elements. One is how we applied mutation, and for that we use a tool and language called Wodl, and then also how we generated tests which were based around counterexamples, for which we use RoboTool and FDR. I'll then move on to give some very initial experimental results and then say a bit about conclusions and future work. So motivation, always motivation for testing shouldn't be difficult, particularly in an area like robotics. So why would we test a system? Well, we're potentially talking about testing simulation systems and also real and actually implementation of physical systems. So there are a number of potential benefits. So within a simulation, for the first level, we can be exploring the behaviors of a model. So we may have produced a model specification, we simulate that. And even if we know the simulation is a correct implementation of the model, if we run tests, we have potential to look out for strange behaviors. So we may have some higher level properties that we would like to check hold. So at a simple level, these things shall not crash into those things, that kind of thing. We might also find cases the developer did not consider. So you could show those to the developer and say, this looks strange, is there a problem? Further down, we'd also then like to be able to apply these tests to real systems. First of all, for software potentially running in a simulation, and then actual physical devices and robots. So in terms of the latter, we also have an opportunity to explore what's called the reality gap, which is where, however good a simulation is, it's not the real world. And you put something that works fine in simulation into the real world, and you see differences of behavior. Here, Mohammed mentioned my interest in search-based testing, and here there's a potential use. So we have the potential to generate tests, execute them on a real system, execute the simulation, look how different they are, and then try to maximize that difference, try to stress the difference between the simulation and the real world. And we haven't got that far yet. At the moment, everything's at the simulation level, but that is further down the line, that is an objective. And then why mutation testing? Well, I'll say a bit more of that in a moment. Essentially an opportunity to see types of faults that one thinks are likely. So our models are in a language formalism called RoboChart. This was developed at the University of York. Please see that Anna and Jim will talk. And essentially they're state machines. And in terms of the mutation work, we're interested in the state behavior. So we have states and we have transitions between states. Transitions between states have actions on them, which we can think of inputs and outputs, or as receiving values from sensors and sending values to actuators. And we can also have actions within states. So an action might, for example, have to occur before we enter a state, or it may occur when we're in a state or when we leave a state. So here's a simple example of a system that is initially in a state off. If it's switched off, on, then it takes off. It's a and then waits a certain period of time to take off properly. It moves until it finds things it's looking for, lands, delivers some items, which takes time, takes off, and essentially returns, and then lands where it came from. So, and then it can repeat that behavior. So the models are state-based. They're cyclic, they have a step semantics, and so time is discrete. So this is all very similar to state charts. A distinct strength, of course, is that they have a formal semantics. So the semantics is provided by mapping the models to CSP. In this case, it's discrete time, so it's a language called TOC CSP. And CSP has models which describe in terms of states and transitions, and with labels, and it has a denotational semantics that allows one to reason about it. So this gives us the potential to have automated testing and sound automated testing. The soundness guaranteed by the formal semantics and reasoning across that. In terms of if we then want to reason about testing and formalize, we'll make the standard minimal test hypothesis, which is the system under test behaves like an unknown model that can be described using the same formalism. So this is in formal testing, this is a standard assumption. Having made that assumption, we don't know what the system, how the system behaves, but we know what the class of behaviors it can have. We can then define what we mean by correctness of a system, and that's defined in terms of implementation relations. So implementation relations say exactly what it means for a system model or behavior to be a valid implementation of a specification. And there are a range of possible options for this, and for this work at the moment we're just looking at time traces. So as implementation is valid if every time trace of the implementation is one of the specification. Further down the line, we want to start looking at richer for notions. We take a mutation approach, as mentioned, so we seed faults. At the moment, we're seeding faults into the RoboChart model. When we seed a fault into the RoboChart model, that defines what's called a mutant, and it's done so via mutation operators. And then at the high level, what we then do is we have mutants of a specification. We try to find test cases that show that these are faulty. And these test cases then are guaranteed to find certain classes of fault. And we apply them to the system. So from a mutation testing perspective, these mutants are what are called first order mutants. We make only one change only. This is traditional in mutation testing, typically justified by two things. One is evidence that if one finds these faults, one tends to find faults that are derived using multiple mutations. And secondly, a view that real systems tend to be similar to correct systems. The benefit of the mutation approach is that we know that if the system passes the test, then it can't have implemented these faulty versions. And importantly, we focused on mutating the RoboChart model. We're not mutating the CSP models. There are two reasons for this. The first is that the system's described at level of RoboChart model, and we have a view that it is likely that faults should be more appropriately described at that level. And the other is simply it should lead to fewer mutants. If we start taking the CSP, which may be infinite model, then we're probably going to get far more mutants, and those extra mutants may be relatively unhelpful. In terms of the overall approach, this is how it operates. So in terms of mutation, it's based around something called WODL. This is a domain-specific language and also a tool, and it's incredibly flexible. So what it takes is it takes our original specification, RoboChart's specification, and it takes the meta model for RoboChart. And the third component it takes is a program. And the flexibility provided Wodl is that it can apply to any language that has a meta model. So the meta model describes the language, the program describes the mutation operators to be applied, and the RoboChart model is the thing to which operators are to be applied. So given these things, Wodl generates a set of mutants. So these are versions of the specification with changes seeded into them. This and the original are fed into RoboTool. RoboTool then analyzes the mutants and rejects those that aren't valid. They, for example, aren't well formed, and generates CSP for the original and also the mutants. We then feed these into FDR. So the specification and a mutant get given to FDR, and FDR is asked, is this mutant a valid implementation of the model? And if the FDR finds it isn't, then it returns a counterexample. So a counterexample is exactly a behavior of the mutant that isn't a valid behavior of the specification. And that then becomes a test case. So at the core of this are a set of tools that allow automation. As mentioned, Wodl is a language, a domain-specific language, and a tool for generating mutants. At the core is a meta model, and it can be applied to any language that has a meta model. And then the operator is defined using a domain-specific language. At the moment, the operators do very simple things. They modify transitions, they change or modify, they delete states. They can change in terms of transition things on clocks and such. So some examples of the kind of things a mutation operator might do. If we take this example again, then here are two operators. The first one takes an entry action and it turns it into a during action. So an entry action is something that must occur before a state is entered. A during action happens within the state. And then the second one changes the source state of a transition. So what can we get? Well, if we start off it here and we change, look at the delivering state, it has an entry action wait delivery. So that means that any transition that we execute going into that state, we have this wait that must occur before the state is entered, and in particular before any leave exit transitions are executed. And that just becomes a during. So now the transition found/land into delivering, once that's executed, we move straight, the model moves straight into the state, and that means it can leave immediately. It doesn't have to wait before it can take off and leave again. And here's an example where the initial starting state of a transition changes, and we can do other things. So this here has deleted some actions from a transition. So we have operators, they generate mutants of RoboChart. These are imported into RoboTool, and RoboTool generates the CSP. So FDR and model checker then, as mentioned, compares them. If there's a counterexample found, then that will form a test case. And the counterexamples are just simple traces. So here's an example from one of the mutants. It's essentially switching on, it takes off, and then it waits 2 time units. Now, this is for an instantiated model in which there's only one duration. The waiting period is only 1 time unit, and so this behavior isn't allowed. If the system did this, then it would be an incorrect behavior. What hasn't been mentioned here, which is important, is the environment. And a potential issue here is that FDR will return any counterexample. I mean, typically we'll try to find shortest counterexample. If the environment has constraints on it, then what we would actually like is a counterexample that makes sense. So once we do this, we have a slightly more complicated setup. So we have the software model again, as usual. We have a mapping that defines how the software controller commands are mapped to robotic commands and events. And then we have an environmental model. And these are all potentially described as CSP processes. And the difference now is that we mutate just the software model. And when we use FDR to compare, we are comparing as a specification, the specification model, the mapping and the environment, with, as a mutant, the mutant model, and the same mapping and environment. And this essentially places a constraint on it that says that any counterexample must be consistent with the mapping and the environment. So this is how we can ensure that we get realistic counterexamples. Test generation, as mentioned, is based upon counterexamples. Essentially, a counterexample is something that shouldn't happen. And so a test is an attempt to make that happen. So we describe the test as simple traces such as this, where essentially our verdict is inconclusive until we've observed the last but one action. And then if we observe the last, it becomes fail. So we say if we observe this prefix, everything but the last, then if we observe the last event, it's a fail. And if we can't observe the last event, it's a pass. That behavior isn't a behavior of the system. We include these inconclusive verdicts because there could be non-determinism. So we could depart from this trace for some other reason. So for example, A2 might be an output, there may be another valid output that could occur. Test execution is then a composition between a system and the test cases. We hide everything except the verdicts, and the verdict of the overall test execution is the final verdict observed. So inconclusive if we diverge earlier, pass if we get to the end but we can't observe the final action, and fail if we observe the incorrect behavior. So that allows us to formalize our test cases and also talk about the test cases we run. In terms of actual test execution, there's a potential inefficiency here, which we intend to address. And this is a result of the non-determinism I mentioned. So if suppose we have two test cases, they both start with A1, and at some point we get a difference. So in the first one, we get some AI, and the second one get AI primed. Now, it might be they're perfectly valid. These are obviously two valid behaviors, and it might be that these are things we can't control from a test case. So there's some non-determinism here. Now, if we execute the first test case, we just consider the first test case, and then we say, get to the point where it should be AI and AI primed happens, then using sequential test cases, at that point we stop. We say inconclusive, verdict, stop. And then we probably keep on applying a test. However, if it was AI primed, then we could continue with our test case T primed. So we could have a whole set of test cases that have some common prefixes that only diverge at points of non-determinism. And if we allow ourselves to move between these, then we potentially have less wasted test execution. And a natural way of doing this was essentially just to combine these to form trees where that's feasible. An open question, very open for me because I don't know FDR well enough is, can we encourage FDR to produce such test cases? Is there some nice trick that can be applied? I will leave that to the FDR experts to look at some point, hopefully. So that's very much future work. Okay, so that's the approach. We start off with a specification model in RoboChart. We generate mutants via Wordle. The mutants are then passed to RoboTool, which will reject those that aren't valid models. For those that are, we generate CSP from the mutant and the original. We use FDR to see if the mutant is a valid refinement. If it isn't, we get a counterexample that becomes a test case. We've carried out some very initial, and I should emphasize very initial experiments, really to get a feeling about what happens. So what we did is we took 3 experimental subjects. For each of those and for each operator, we generated all the mutants up to a bound of 100. So Wordle allows one to set a bound. So this is just to make the experiment more scalable. For each of the mutants generated, we passed that to RoboTool, determined how many were valid. And there were 2 potential reasons for being invalid. A mutant might fail the meta model, or it may not be well formed. For those, and in one of these 3 models, we then passed the mutants, the valid mutants and the specification to FDR to determine how many actually represented faults were not refinements of the model. So I will very quickly, I'll run through these. We had 3 experimental subjects. If we look at them, they vary in size, none of them massive. These obviously are metrics regarding the RoboChart model. So number of states varying between 4 and 36, and number of transitions from 5 to 75. So they give us some idea of what happens as we scale up. And here are the mutation operators we use. I'm not going to go through them all. The names are moderately intuitive. Where the name operator starts with R, it means remove, and when it starts with M, it means modify. So, for example, we have operations to modify the source of a transition. We have an operator to remove a weight. These kind of things. And if we look at how many mutants we get, then this is the results we had. So we have a number of for the largest model, which is RoboVacuum, we have a number of operators that get to 100 mutants. And we could explore further to see whether it will turn into 1,000 or 1,000,000. I don't think 1,000,000. For the intermediary side, the foraging robot, we have 3 operators that get to 100, and for the very small, example, drone, we have none. And then we have a number of operators that lead to fewer. So you see, there's a sort of variety of patterns, as you'd expect, because different models have different sets of features. So, for example, here we have one operator that for RoboVacuum generates 100 and for nothing else, and produces none for the others. So this is obviously mutating an operator elements that are in one model, but not in the others. If we then look at what happens if we ask whether mutants are valid, then this is the behavior. So for each model, an operator, we've got 3 numbers: the number of mutants generated, then the number that satisfied the meta model, and then the number of those that satisfied the meta model that were also well formed. So there are examples where pretty much everything is well formed. So for example, this again, this modify elements enumeration, they're all well formed. And then some extreme examples. So removing state was never valid. This is despite deleting and corresponding transitions. So in all cases, something went wrong. And then there are some intermediary where we modify source and targets, and some of them are valid and some aren't. So it's a very mixed pattern so far. If we go to the drone example, our small example, then we looked at how many were refinements and how many weren't refinements. So here we see that a number of them produced useful at the level of generate test cases mutants. So for example, modify the target transition. In this case, none of the valid mutants were refinements, so all 15 would lead to test cases. In contrast, if we look at, well, modify the source, then half of them were valid and half of them were faulty. So in that case, half of them would generate test cases and the other half provide no assistance at all. And overall, we see that a bit over half would have led to test cases. So we, at the end of this process, for this small example, we end up with 53 test cases automatically generated. Okay, so I said it'd be quick, and that was quicker than I expected, so apologies. Future work, there are a number of lines of future work. Probably the most important is going to be additional studies using new case studies. The semantics we've looked at so far is just traces. We've not used any notional refusal. So we're not allowing our tester to observe that a system can't do something, for example. Can't accept some input, can't produce. There are likely to be scalability issues. So our experience so far is that for the smallest example, FDR is fine. For the larger examples, once we start trying to include an environmental model and composing models, FDR really struggles. Now, this may be something that can be resolved via some optimizations. It may be that we simply have to look at alternative solution mechanisms. So maybe theorem provers will help, maybe constraint solvers will help. Ultimately, I suspect there's going to be an element of running simulations and using something like meta-heuristic search as a dynamic technique, so we get feedback. There's the question of complete test techniques, and in some ways, sort of particularly interesting is when we move on to probabilities and also continuous variables. At the moment, variables where they were potentially continuously discretized, which of course doesn't help with model size. That leads to a blow up in terms of semantics. Do we get benefits by treating them as continuous variables? We've got hybrid automata, for example, and how can we handle probabilities? Jim's looking at probabilities, and that will feed into this. Okay, so a very quick run through the high-level approach. The approach overall is we use this language and model model generate mutants. The mutants represent potential faults in an original model. We generate the mutants, use it, and then pass them to RoboTool. The RoboTool checks validity. For the valid ones are passed to FDR along with the CSP, passed to FDR along with the CSP of the original. Counterexamples define tests that are sound and guaranteed to represent faults. And in terms of experiments, we have sort of some initially variable patterns, but also some evidence of scalability in terms of FDR. And lots more things that need doing. Okay, so thank you very much. Again, a bit faster than I was anticipating. I wasn't expecting to use the hour, but that gives us plenty of time for any questions.
Yes, I think there is ample opportunity for discussions. So are there any questions to start the discussion? I have many, but I will wait for a couple of seconds until perhaps someone else wants to start. If there are no questions, let me ask the first question and hopefully others will join in. So regarding the use of FDR, so model checking is quite a heavy tool for generating counterexample. Do you see any opportunities in using like search-based techniques, some more lightweight techniques to find a counterexample?
Yeah, absolutely. That's a good question. I think ultimately we're going to, I think there are lots of benefits to doing that. If something like FDR works, then great. But such techniques will only scale so far. And I think also those search-based techniques provide a number of potential additional benefits. So we can try searching for scenarios that have particularly interesting properties, or that come close to or succeed in breaking desired properties of the system model. So yes, absolutely. Yes, I think that's going to be crucial.
Have you hit the boundaries of FDR already or not?
Okay, so with a larger example and an environmental model, so we have the composition, FDR didn't really scale. Now, that may be that we need to do some optimizations, and there is an issue around us discretizing continuous variables, which leads to an explosion. But yes, we have already reached some scalability boundaries, and we're planning to explore use of hybrid model checkers. But I suspect also they will only scale so far. Yeah.
I guess Anna has a question. Anna, would you like to ask a question?
No, Mohammed, I was about to say we reached the limits because of discretization. Just as I was about to make that point, Rob already covered it, of course. So there is no way that we can, well, we haven't, to be honest, we haven't done anything in terms of optimization of the model, but we don't feel encouraged by trying to deal with discretized models. It's just not, the discretization would be just something that we would do for validation anyway. So we don't feel encouraged to pursue that.
Very interesting. Are there any further questions? Hi, Jim. Yes, Jim, please go ahead. You are muted, Jim, sorry.
Thank you. Classic error. Hi, Rob. Your talk was entitled Mutation for Robotics. What if you have learning components?
No, that's a very good question. The first thing is, do you have a specification of your learning components? And if the answer is you do, then great. And if the answer is you don't, then we have some interesting questions. I would say there are a few options. And part of my answer is I don't know, but I think a number of options. One is that we might want to bound the valid behaviors of those learning components, and then we can reason about a system that includes learning components that sit within those bounds. Another thing we might do is we might try to learn about our learning components and apply testing to them and some sort of inductive process where we end up with a model of our learning components. So that would be my feeling. I guess the answer that says don't isn't going to wash.
No.
If you've got better thoughts, I'd be really interested, or other thoughts.
Another time, perhaps.
Yeah, absolutely. Now Mohammed's muted.
Sorry, I was saying Seamus has raised his hand. Seamus, would you like to ask your question?
Yeah, sure. Thanks, Rob, for a very interesting talk. I just wanted to ask in terms of the results you showed about the three categories. Why do you have a not well-formed mutation? Is it because of why do you have not well-formed test cases? Is it because of mainly of the removal I was just wondering why that might be incorrectly formed test cases.
Yeah, so it's actually the mutants that aren't well formed, and there are certain well formedness properties in RoboChart, and Anna could tell you much better than I could what they are. But I think, for example, they should be deadlock free, and should imagine. I can't remember, I should check this, but you could have something where states aren't reachable anymore, for example. So there are a number of properties. The meta model describes the syntactic elements and how you can connect them, and the well-formedness are then semantic properties of valid models.
Okay, so following from that, are there any thoughts to capture somehow these demanding properties in order to steer, let's say, the mutation in a more meaningful way, or is it too difficult to do it?
I think it'd be really difficult to do all of them, but we might be able to assign mutation operators that are less likely to return invalid mutants, and I think that would be really useful. Yeah, we've made no attempts to do that, and I think that would be a useful thing to do.
Okay, thank you.
I think there is a trade-off, isn't there? You can create more complex mutation operators that will then ensure well-formedness to a certain point. But you can then have very simple mutators that they may, for example, introduce the use of a variable that's not declared. And if that's a very crude example. But in general, you would need theorem proving to establish all the cases. For example, when we have a junction in a state machine, the guards of the transitions that come out of the junction have to form a cover. They have to cover all the possible cases, and that's something that's easy to break with mutation, just by negating some of these guards, but not all, and so on. So it's a trade-off.
Okay, further questions? I have one further question, if you don't mind, Rob. So I was thinking of learning. You mentioned that also in an answer to Jim. So I think the technology you have developed so far, this setup, could also be used to learn RoboChart models of implementations, right? So you start from a model, you mutate that, and then you generate test cases as kind of membership queries to the system on the learning. Have you thought about that?
Not really, but you're right. A little bit like a variance on sort of the L star.
Exactly. Yeah, I was thinking of the star. Yeah.
Yeah, absolutely. That makes a lot of sense, and we've not tried that at all. But yes, and it might be a way of learning. If you had a model of an earlier version, it might be a way also of learning a new model of an updated system, which may be an easier problem.
Yeah, so actually we have a couple of recent work on learning the update, so elaborate on that. Yes, and I think there is a challenge. Most of the learning techniques talk about untimed systems. Here, learning about time might have some peculiarities, but
yeah, absolutely.
Okay, are there any further questions? Still have a few minutes. Any further questions? If there are no further questions, thank you very much, Rob. It was an inspiring talk. I think there are lots of things to follow up and hopefully lots of opportunities to collaborate within the lifetime of the project. So thanks again, Rob. We are very much looking forward to collaborating with you and doing some very exciting research. Thank you all for being here. We have the next speaker. So in 2 weeks, Rob Richardson, who is coming from the other side of the reality gap, will talk about building robots for the real world. The announcement for the talk will go out tomorrow through the mailing list. If you are not a member of the mailing list, please drop me a line and I would be very happy to add you to the mailing list. And I wish you all a very nice evening. Thank you again, Rob, for this very interesting talk.
Okay, and thank you.
Thanks. Bye for now.
Bye.
Bye, everyone.
Bye.
Bye.
Bye.